So in the last session we have discussed the continuous function and the basic properties of continuous functions. Also the composition of two continuous functions and addition of and scalar multiplication of continuous functions. Okay. In fact, remember we have discussed something called gluing of two continuous functions. Okay. So just to recall all these things, so gluing means suppose we have two sets, let's say A and B, and such that from A to another set we have one function. Let's say it is my x, here it is my function f, and here it is my function b. G. Of course, A comma B both are subset of x1 is a topological space, and such that F and G both agree in this particular region, the intersection region, right? That means F restricted at A intersection B is same as G restricted at A intersection B. Then I can glue all these two maps F and G and can get another map H is mapping from A union B to X such that H restricted at A it is F and H restricted at B this is G. Alright, so this much we have done in our last session. Now we will use these continuous functions, property of continuous functions, to define some more basic identification of two topological spaces, and one of the most importantly, this one is something called homeomorphism. All right, so first let us start with the basic motivation. So suppose we have, let us consider that V is a vector space and U is another vector space, both are over the base field capital F, right? For example, let's consider dimension of V over F is same as dimension of U over F. This is same N. Okay, so they as both as same dimensional vector spaces over a particular field F, then of course we can say that V is isomorphic to U. So that means we can define, we have a linear map which is T from V to U such that number 1 T is linear, number 2 T is bijective, and number 3 the inverse of T is also linear map. Okay, in fact these two properties are enough to check, because once it is bijective then the inverse of this linear map is always the inverse map is always a linear transformation, right? But in general these are the things that one need to check. So the same thing in case of vector spaces, we can transfer some element from one vector space to another vector space via these linear maps. But in case of topological space, we have the same notion by using, we have the same notion via the continuous maps. So just the same thing will happen here. Suppose X and Y both are two topological spaces. Okay, so as these two are topological spaces, so there exist, we say that, so we say that f is a function from x to y is, we say that if x is homeomorphic to y, if there exists a continuous function f from x to y such that, so of course, first of all, f is continuous function. Number two, f is bijective map. And number three, f inverse is continuous. So all these three properties are there. Okay. So just to have some more intuition that, so what does this continuous function means suppose, so if we have, let's say, u is open set of y, then f inverse u, this is open in x. So this means that bijectivity means open, it is 1 1 and on to, that is very trivial, nothing. But what does this mean? So this means that when, so you see that f inverse is defined from y to x. Okay, so that means suppose we take any open set, let's say ux, this is open in x, then f inverse whole inverse of ux, this is open in y. Now as f is bijective, so f inverse is exists, so f inverse of whole inverse, it is nothing but f of ux, this is open in y. So that means this particular criteria is implying that f must be an open subset. Okay, so all these three properties are there. All right, so this is this particular f, this is said, which is basically a bridge between two topological spaces, this is said to be the homeomorphism. Okay, so there's a very beautiful exercise, you can just try it at your own. That suppose top be the let's say this is be the category of all topological spaces, then we define a different relation, let's say this, on the top, it means it is a base underlying set, so of the category. So I mean, you know that category is basically consisted of a underlying set and a morphism, right? So a composition is a morphism. So we define a relation, let's say it is tilde on top, such that any two topological spaces x1 is related to x2 if and only if x1 and x2 are homeomorphic. So check this relation is an equivalence relation. Okay, and just try to find out what is the set of all equivalence classes, which is top x, top sigma, which is equivalence classes. So the basic equivalence class of one particular x. The set of all homotopy classes you can consider as homotopy classes. Okay, these are the homotopy classes. This is an exercise, you can check it by your own. Okay, so for example, let us consider some example. So let us consider identity map of x from x to x in topological space. This is a very trivial and most common. So this is of course a homeomorphism. Okay, or if we have, let's say, x equal to r, so then we can consider the translation. Suppose f is a mapping from r to r such that f of smaller equal to r plus delta, where delta is fixed. Okay, then delta is fixed. Okay, next suppose if is a you can define, let's say, scalar multiplication if is a mapping from r to r such that f of r equals delta r, where delta is not equal to 0, and here is also fixed. Next, suppose x equals to c and y equals r2. So then define f is a mapping from c to r2 such that f of a plus ib is nothing but a comma b. Okay, this is how one can define the scalar multiplication map. All right, so some non-examples. Let us begin with here. So let's give some explanation. So some basic explanations are something like this. Suppose we consider, let's say, the translation property. Okay, so that means if you have, let's say, r like this, it is singleton 0 to plus infinity is minus infinity. So if you take any point here, it will take up to something like this. So if it is r, so it is r plus delta. So that is the translation part. So every point is basically running over like that. So these are segments. Scalar multiplication is also something like that. And once you have c2 in r2, so in r2 it means that suppose you have, it is my r2, so in c the argand pin is like this, right? So a comma ib, so is a plus ib, this is argz. All right, so this can be identified as a comma b. Okay, this is how one can define the homeomorphisms, and you can check all these are homeomorphisms. So these are basic checking. These two are very easy. nothing to prove at all, but there you may have to take some more calculations over there, but it is also very easy. Like if you consider any, I mean, if you have to just consider what are the basic open sets in R2, then you can easily cook up that in C as well. Okay, all right. So again, see, so you see that what are the cases we have defined, like R to R is basically taking this entire real number to onto itself, entire real number itself. But you can think that suppose if you may be able to define some map such that, I mean, such some homeomorphism such that this entire real line be shifted like from here to like that, right? Means suppose you have it like this, so I will take it starting from here itself. That means basically I want to define a homeomorphism. Suppose this is another example. Homeomorphism, let's say R to R strictly larger than 0. So what homeomorphism that we can define? So we can define this, of course we announcing it is to be a homeomorphism, so that defined to fx e to the power x, because you always know that it cannot be 0 itself or cannot be 1 negative itself, because exponential function always strictly 0, right? And in fact it is in fact this is a homeomorphism, because I mean because it is injective also as well, and surjective it of course. So nothing to prove homeomorphism itself. And of course R singular larger than U is associated with subspace topology. Okay, all right. Okay, now there is a proposition. Suppose that x and y, these two are topological spaces. Okay, so we define that set of all A alpha such that alpha is any index set gamma. This is be family of subsets of x. Okay, such that x equals union of alpha belongs to gamma A alpha. So then let f is a mapping from x to y be continuous functions such that f restricted at A alpha is mapping from A alpha to y is continuous. Okay, then condition 1 is, suppose this gamma is finite set, is finite index set. Okay, and if each A alpha is closed, then f is continuous. So basically it is extension version of extended version of pasting lemma. Okay. So suppose consider that gamma is alpha 1, alpha 2 up to alpha n. Okay. So we consider that x equals a alpha 1 union a alpha n. Okay. So if it is my x, suppose we consider that a alpha 1 union with a alpha 2. Okay. So we have, so let us consider that we define phi1 to be af restricted a alpha 1. Okay. And phi of t equals to f restricted a alpha 2 and so on up to phi n restricted equal to f restricted a alpha n. Okay. These are the notations we have defined. So phi1 is defined from a alpha 1 to, let's say, y, and phi2 is defined from a alpha t to y. So what is, suppose small x belongs to a alpha 1 intersection a alpha 2. So small phi1 of x is nothing but f restricted a alpha 1 of x. So it is of course f of x, right? And similarly phi2 of x, it is f of x as well, right? Because f is a fixed function. So of course we can join them up, like you can get f of a alpha 1 union a alpha 2 of x, which is f of yesterday alpha 1 of x and a alpha 2 of x. Okay, means it is basically phi1 2 by pasting lemma. By pasting lemma. Okay. So similarly, one side is clear. Again, we have f of a alpha 1 union a alpha 2 union with a alpha 3, which is same as f restricted a alpha 1 of x when x belongs to a alpha 1, because I will just take a alpha 1 by alpha 2x, right? And then f restricted a alpha 2 of x when x belongs to a alpha 2. There similarly we can get, and f restricted a alpha 3 of x belongs to a alpha 3. So then we are done, right? So thus if we go on by up to n steps, so up to nth step I will get f union f of union with I equals 1 to n a alpha I of x is same as a alpha I of x where x belongs to alpha I. So now if we, now this is my exactly f, right? Because if you take any small x belongs to x, so it has to must be small f of x. Okay, because x must be in some of the f alpha is a alpha is. Okay, so this is one can define. So this is exactly same as f. So this is my f. So in fact this is continuous function. Okay, so this is how one can define the extended version of the pasting lemma. But the question is that so what about what if the collection is infinite? So maybe countable or